Hello and welcome to Completely Electrical STEM Show. Some more cable design videos here, and this time it's a resistive load. A 6 kilowatt curtain heater that you might find over a shop doorway or something like that. Again, I'm going to go through both methods for both the live cable sizing and the CPC sizing. And so hopefully by the time you get through all these videos, you'll start to piece it all together and maybe start to make sense. But the best way to learn this stuff is just play with it, ask yourself what that means, you know, what does that value mean, what's going to happen to the circuit, just try and get to know it a little bit better. So join me down there. Okay, so resistive load now then, and this is what we've got. We've got a 6 kilowatt curtain heater, 230 volts, 50 hertz, single phase supply, and the ZE is 0.10. And then that's going to be installed in existing trunking with 2 other circuits, and it will also go through 100mm thermal insulation through a wall. So we've got the trunking coming along the wall through a wall that's got this insulation in, pops out the other side. Obviously observe your fire barriers, but let's start with our design current. Always start there, and with the resistive load it's quite straightforward. P over V, which in this case we've got 6 kilowatts, so 6,000 divided by 230, you get 26.1 amps. If this was 3-phase, then this would be shared between them, and that's why we can have smaller cables for 3-phase, but we've got 3 of them, so cost savings, don't know, got to weigh it up. So 26.1 amps our design current. It's a resistive load, so a B type will be adequate, and we want to go up to the next one up from that really, which would be a 32. I think in this case we could do an RCBO. I can't really think of any issues the curtain heater might present that might cause any nuisance tripping or anything, so RCBO, why not? So our IN then is 32 amps. Now we're going to have an insulation factor and a grouping factor. Now I'm just going to try and keep that quite simple really. So we're going to use the factors in where is it? CI. Now that's not near the other grouping factors in the regs book. It's in 523. Hold on. 523.9. There we go. Got there in the end. I'm telling you, the reg stuff, it's in your head 1 minute and then it falls out. Anyway, table 52.2 is what I'm after. Now it says essentially, if you read that section, so 523.9, let me just get it. It starts off by saying a cable should preferably not be installed in a location where it's liable to be covered by thermal insulation. For obvious reasons really, it's going to suffocate, isn't it? It's going to not be able to breathe. And you keep reading down here, and it essentially says if your single cable is likely to be totally surrounded by thermal insulating material over length of 0.5 meters, so just 500 mil, the current carrying capacity should be taken in the absence of more precise information as 0.5 times the current carrying capacity. So it halves the current carrying capacity, which basically means we're going to have twice the cross-sectional area. So, you know, avoiding insulation is definitely the way to go. There is a note there about thermal conductivity worth reading, and also that table is limited to conductor size up to 10 mil. But it's going to give us a good starting point. So having a look at that table then, it tells us the length of insulation 100 mil, we get a derating factor of 0.78. And I'll just reiterate that yes, there's loads more to learn about this, as there is with the grouping factors. I'm just keeping it simple for now because this is level 3. The grouping factor, as it was before, it's table 4C1, which is at the back again. Appendix 4. Oh, come on. I wish I was faster at flicking pages. Well, I mean, I know what it is. It's going to be the same, isn't it? It's 0.7. There we go. So page 396. And we're still bunched in air on a surface embedded or enclosed when trunking. And we've got two other circuits in that trunking, which makes 3. So 0.7 is our number. Okay, now those are going to occur simultaneously, aren't they? So we need to apply both of them there. Yowzers, that's going to have quite an effect. With these grouping factors, incidentally, if say, I don't know, there was no grouping here, and it, yeah, we got the CI occurring there, and then it only grouped there. Yeah, that makes more sense, great. Then essentially we would take whatever the worst one is. So in this case, that would be the grouping factor. 0.7 is going to increase our CSA more than 0.78. Essentially, you know, under 1, the closer you get to 0.5, the closer you are to doubling the CSA. So it's only the worst point on the circuit. That's what I'm trying to say. So any factors at the worst point, that's the ones you apply, because that's going to essentially kind of create a bit more resistance. But that would be the same throughout the circuit. The current runs in the circuit the same. So if we calculate for the worst point, then the rest of it will be okay. That's the idea. And so, you know, in our case, we are going to apply these together because the grouping is there. We've got the circuits running through and the insulation is there. So unfortunately, that's what we're going to have to do. So we've got 32.78 times 0.7, which gives us an IZ of probably quite a lot. $58.6. Wow, that's what it says. So next, we're doing method 1 for our live tables. So we're going to go to the current carrying capacity tables. Sticking with singles for now. I'm going to stick with 70 degrees. Keep things simple. Now, single phase in a trunking on a wall. Down here, and we're looking for quite a lot, aren't we? 58. Oh look, just missed 10 mil there. 58.6, and that's where it's worth getting involved with these grouping factors, because we might be able to like alter that if only we knew more. But we don't, so we got to go with this 58.6, and it says essentially that we're looking for a 16 mil. Wowzers. And that's got an IT of 76 amps. So 16 mil IT 76 amps, and that was column 4, table 4D 1A. Okay, put a page number, but that'll just be for you really. Okay, so now that's what we got. No chance of any overload, so you don't have to worry about that. That's good. And now we just need to check it for volt drop. Now, millivolt per amp per meter for that. Go to the next page. Single phase A and B, 16 mil, 2.8 is our millivolt per amp per meter number. So I'll just remind you of the equation. So we can put this in, so 2.8 times the length. Damn it, I know I forgot something. Let's say, well, we'll say 15 meters, shall we? Why not? Design current, then length, that's what I said. 15 meters over 1,000. It's probably going to be okay. 2.8 times 26.1 times 15 over 1,000. 1.1 volts. But you probably knew that with the size of the cable. And the actual load is pretty low, so because ultimately it's that. Right, so that's that. That's 16 mil. Jesus. Or cheeses. Okay, so I'll tell you what, let's just turn it open. Oh, that looks bad. Let's do method 2 then. So again, that was just flipping it on its head really and just going for volt drop. But probably not going to work. It's probably going to end up back and forth again. So 6 kilowatt. ZE was 0.12, but that isn't relevant. Our CI was 0.78, CG 0.7, length was 15 meters, design current was 26.1 amps. Okay, so where do we start? Well, we've done the design current, done that, and we know the IN, 32. So that's when we jump onto that volt drop. So rearranging that volt drop again, max millivolt per amp per meter. God, slow down, Craig. Is equal to our maximum volt drop, single phase now, it's still power, so it's 5% of 230 volts, which is 11.5 volts. So it's the maximum allowed volt drop times 1,000 divided by design current times length. And you know, the rearranging of that is fairly straightforward. And I've done that in the other video. So filling in what we know then, we know 11.5, we know the number 1,000, we know our design current, that's 26.1, and we know our length is 15. So our maximum millivolt per amp per meter value then would be 29.37. That's the maximum, so any cable under that will be allowed. Here we are. Was it 29.37? So it can't be a 1 mil, but a 1.5 would work. But look, I mean, you know, we know it ended up as 16 mil, so I think we know where this is going to go. So we're saying 1.5 mil. Well, I'll just go through the method anyway. Now we need to know the IT of a 1.5 mil in those conditions. So reference method B, single phase, 1.5. We've got an IT of 17.5, which is already less than our design current, so we know this isn't going to work. 17.5 amps. Then check. So in our case, 17.5 times 0.78 times 0.7. It's not going to work, is it? Now this has to obviously equal 32 amps in our case. And predictably, it doesn't. No good. So, you know, we'd go up to a sensible size, blah, 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 blah. Well, let's go up to 10 mil, because, you know, we know that that was fairly close. Let's just see how close it would be. So the IT of 10 mil then, 57. So let's start again. 57 times 0.78 times 0.7. What do we get? $31.12. So, you know, if you had a bit more knowledge about these factors and you were confident that we could tweak them a bit safely, then, you know, you might be able to get down a whole cable size there. That could be a real bonus, couldn't it? 16 mil cable ain't cheap. I mean, nor is 10 mil at the moment, but you know what I mean. Block of flats, that would add up. So what did that come to? 31.1. So it's still not the same because our IZ is less than our IN, and it has to be the other way round. IZ must be the same or more than IM. If it was overload, we said that it's the IZ would have to be IN times 1.45, but we don't have to worry about it in this case. So, you know, again, we got there pretty quick the first way. There we go. That's the method 2 sorted. So that's our live cables. And then the CPCs, we already know we got that, so that's our live and our neutral. So now we've just got to choose the CPC. And for that, we're going to need either the on-site guide tables or guidance note 3, table B1, I think. Yes. So what are we checking for with CPC? We need to make sure that it complies in terms of its earth fault loop. So we need to know our max ZS, our target, if you like. And we need to make sure it complies with thermal constraints. So during the fault, is the CPC going to destroy itself before it disconnects? That's what we're after. So again, there's two methods. We can either just take a stab in the dark and check it for compliance, or we can rearrange and find out our maximum R1, R2, which in turn tells us our maximum milliohm per meter value, and then we can choose a cable fairly quickly that way. So first step then, we need our maximum ZS. Now we had a 32 amp B type, and I'll just do that equation anyway again. It's IA, so it's the trip current required to trip the breaker instantaneously. And to get that, it's its rating times the multiplier based on you know, whether it's a B type, a C type, or a D type. So in this case, it would be 32 times 5. So we end up with 218.5 volts. This is a C min factor, by the way. It just drops the voltage a little bit for the worst case fault current. If you've got lower voltage, you're going to have a lower fault current. So if it complies with that, chances are we're all good. And 32 times 5 is 160. 208.5 and 1.37. Really need to mix these up. 1.37 then, that's our target. But you know, we probably want to do better than that really. And we know our ZE, that was 0.12. Yes, 0.12. So if we take our max allowed ZS, get rid of the ZE that we've got, so deduct that, that leaves us with a maximum R1, R2 that we've got to work with. So 1.25 ohms. Okay, now rearranging this formula, very similar to volt drop really. I'll put TF, temperature factor there. So, you know, that would end up there, they would divide down, and you end up pretty much, that's a max milliohm per meter. Max R1 plus R2 times 1000 divided by length times your temperature factor. So that's the equation we're going to be using. And we already know our live cables, so once we've got that, we can just find a milliohm per meter value that matches. So we're probably up here somewhere, 16 and something. But we'll probably find that, you know, we can get quite small with this like before. And then it's just a decision about, you know, mechanical size really, and maybe terminal size if it's got big terminals in the load. I don't know, it might be easier just to run a big cable, but you've got costs to consider all the time. So anyway, let's calculate this. So we know our maximum R1, R2, so 1.25 times 1000 over our length, which was 15 meters, times our temperature factor, which is going to be 1.2, but it's table B3 or I3, I think, in the on-site guide. And although we're singles, we're using this incorporated in a cable or bunched. It is near to the live conductors, so we're going to assume that that's the right one, because it is. Equals, so I'm getting a maximum milliohm per meter value of 69.44. Yeah, right. Any of them really, isn't it? So let's just try one, shall I? Let's go with a 1 mil. Okay, so this is where we'd calculate our actual R1, R2, and then our actual ZS and prove that it's compliant. So actual. So as I say, we'll start with 1 mil. It seems certain that most of them are going to work because they're all under this number. Max. So milliohm per meter times length times 1.2 over 1000. So we've got 16 mil on its own is 1.15, and then 1 mil on its own is 18.1. So to get our milliohm per meter as a live and CPC, we just add them together. 19.25 milliohms per meter. So put that in, times our length, times our temperature factor. Let's see what we get. .35 ohms. So it's good. So our actual ZS then, ZE plus R1 plus RT, that would be 0.12 ohms for our ZE plus our R1 R2 of 0.35, which gives us 0.47 ohms. Clearly much less than that, so it's all good. Then our last check for the CPC would be our adiabatic, and that's to check to see if our cable size, the 1mm there, is going to survive that treatment, really, that amount of fault current going through it. And with the adiabatic, you know, the lower the ZS, you know, the more current that's going to flow, and so the more energy is going to go through that poor little 1mm, and we want to make sure it's going to survive. And it's the insulation we're really thinking about here. The copper would probably survive. It's the insulation that we don't want to get damaged, because if it gets damaged, you can't trust it again, can you? So it needs to be within its kind of tolerances and safe limits. So we're not thinking the copper's going to melt here. I mean, it could in extreme cases, obviously, but what we're really seeing is about the insulation around it. So we need our T will be 0.1 because we're complying with ZS, and if you go to those time current charts, it will tell you that. It will trip instantaneously as long as it's under the max ZS. K is 115 again, 54.3, I think. Yeah, table 54.3. And our I, again, I'm just going to keep 230 volts over our ZS. So 230 over 0.47 will give us a full current then. So this is right at the end of the circuit, you know, substation, DNO's cut out, breaker. Right at the end of the circuit, got our heater load, neutral coming back, then our CPC is kind of connected onto that. Let's say we've got TNS. You know, what we're saying is if the live touches the earth, you know, this is how much fault current is going to flow. And it's telling us 489.4 amps. So, what effect does that have? Okay, I think I've just got room for that. So, our minimum CPC we could have then 489.4 squared times 0.1 divided by 115. And just remember that this hat is only on the top line, it's not going on the bottom line. So, square root of 489.4 squared times 0.1. So it's saying 1.35 mil. You know, and that's, so it's within acceptable tolerances because we, oh no it's not, is it? We went for a 1 mil. Oh, so it fails. Brilliant. Oh, I love it when things fail. Oh, that means we've got to go back then. So we need to choose next size up. So we know 1.5 will work with the adiabatic at the moment, but we'd have to recalculate that ZS. So 1 mil's no good here. So where are we with our new R1, R2? I'll just kind of section this bit off a sec. See if I've got room here. So new R1, R2. So 16 mil as 1.15 milliamp per meter. Let's say 1.5, so that's 12.1 milliamp per meter. Times it by our length, temperature factor 1000. So our new R1, R2 would be less. So 0.24, which means our new ZS would be 0.12 plus 0.24, 0.36. So that means new fault current, 0.36 clearly still complies. So that fault current's now gone up to 638.9 amps. So our new fault current, 638.9. And then we'd have to put that back into the adiabatic now to make sure, you know, this is still okay, maybe, because this might mean that the 1.5 is not big enough. So let's try it. 638.9 squared times 0.1 over 115. So now it's saying minimum's 1.75, so the 1.5 doesn't work. Oh no. So, you know, should we just jump to maybe a more sensible kind of option? And this is a great example of where, you know, the ZS might comply, but your adiabatic doesn't. So, you know, you can't just go by this all the time. So we jump up to a more kind of sensible combination, really. The twin and earth is normally quite a good guide, really. If your live cable is 2.5, you know, most twin and earths is not quite half, but a little bit more than half. And that's quite a good guide, really. So 4mm, 2.5, 2.5, 1.5, 6mm, 4mm, or actually 2.5. I think there's two versions actually. So let's go with a, you know, a 16 and a 6. So that would be a milliamp per meter of 4.23. Now I'm kind of running out of space. So with new 1R2. So this is with a 16 and a 6mm CPC. We've got a milliamp per meter for 16/6mm of 4.23 times length times temperature factor over 1000. So our new R1R2 then, very low, 0.08 ohms, which means our new ZS will be 0.12 plus 0.08. A half, which means a new fault current will be 230 divided by half. Is that right? That can't be right. 0.08 plus 0.12. 0.2 numbers. So 230 divided by 0.2. There we go. That looks a bit better. You've always got to be on your guard. It's so easy to kind of make a silly error. It just throws you off. Just read that fraction wrong. So a much bigger fault current now. Let's hope a 6mm can cope with that. So our new minimum then, 1150 squared. Definitely going to disconnect instantly with that. There we go. 3.16 mil. So there you go. That's quite a good one actually. I didn't realise it was actually going to turn out like that. But you can see that, you know, just because your ZS complies, it doesn't mean your adiabatic's going to comply at all. And then just going up, you know, just one size, thinking that, you know, if you calculated it for a 1mm, you might look at that and just go, 1.5 then. Well, no, that didn't work, did it? So it came out as, I better put that in really. I'll just redo that. But yeah, it came out as like 1.7. So you really got to keep checking these things. Yeah, 1.75. So the 1.5 wouldn't have been enough. And that's when we jumped to a more kind of sensible combo that, you know, makes sort of sense in your head, doesn't it, logically? And now it works. Now you probably could go down to a 4mm, but you know, to be honest, I think I'll be tired by that point. I'll just go, oh, 6 will do. And at the end of the day, as long as this all complies, then the circuit should work. That's what we're after. So it's always 2 checks for CPC. It's your ZS, but it's also it's adiabatic. I'm quite pleased with that example actually. Now just yeah, let's leave it there, eh? I'll see you next time. I'm gonna just try and think of some more wacky examples really, and the kind of things that people ask all the time. Ring circuits is one of them. And key to that really is knowing that those standard circuits, they assume a design current of about 20 amps. And I'm not sure any ring circuits actually comply in the real world actually. I've seen them a lot longer than they should be. Yeah, bit of a problem really, but they're going out of fashion, so is it worth teaching it? Yeah, I suppose so. I'll get round to it one day. Anyway, yeah, see you later. Bye.